Okay, now you look here. Suppose I differentiate this partially, actually I should have put this partially with respect to x. What do I get using the formula for differentiation of product of two functions? First I will get e to the power minus xy. Then since y is considered to be constant, it's with respect to x, so minus xy e to the power minus xy. So I am getting this integrand. So that means this integration is given by this x times e to the power minus xy, where the limits are x equal to 0 to x equal to infinity. Now, when we put x equal to infinity, we don't actually put x equal to infinity, it's rather the limit. Limit x tends to infinity, x times e to the power minus xy, minus, when we put 0, there is no problem. So 0, so this becomes 0. Now we have to find this limit. Okay, now in finding this limit, what I do, I write it like this, and then I use the series expansion for e to the power xy. So this becomes what? X divided by 1 plus xy by 1 factorial plus x square y square by 2 factorial plus x cube by 3 factorial, etc. So this calculation ultimately becomes limit x tends to infinity. Now I can divide both the numerator and denominator by x. Why? Because x is a real number. X is not equal to infinity, but x is very large. 1 by x plus y by 1 factorial plus x y square divided by 2 factorial plus x square y cube divided by 3 factorial, etc. Okay. Now if I think of the limit, as x approaches infinity, 1 by x approaches 0 plus y by 1 factorial, the other terms all approach infinity because in them x is in the numerator. So as a whole, the denominator is it becomes infinitely large, larger and larger, so the limit is 0. Okay, so the inner integral, its value is actually equal to 0. And then the outer integral will also be 0. So this integral is equal to 0. Now we switch the order of integration and then calculate. Now what we calculate? We want to calculate this. E to the power minus xy minus to the power minus xy dy dx. Now this one we want to calculate. Now for this one, we can see that if we differentiate this function partially with respect to y, what do we get? E to the power minus xy minus, now x is considered to be constant, so xy e to the power minus xy, that same integrand we are getting. But now the function from which we are getting that integrand, that is different. So for the inner integral, this is 0 to 1. Oh, I don't have to write the integration again. It's y times e to the power minus xy, where y is changing from 0 to 1. Okay. Now, if I put y equal to 1, I get e to the power minus x. Minus, if I put y equal to 0, then this vanishes. So, we are calculating now the outer integral becomes e to the power minus x dx, which is nothing but minus e to the power minus x, where x goes from 0 to infinity. E to the power minus infinity is 0. That is not true actually. E to the power minus infinity is not 0, but this limit is 0. This limit is 0 plus e to the power minus 0. So this is equal to 1. So we see that this integral is equal to 1. They are not equal. This is 0, this is 1. So the very useful technique or trick of interchanging the integrals, because sometimes what happens, we have an integral that is lying on the outside, which is easier to calculate at first, and then we can use that to calculate the other integral. So that sometimes is not possible, like in this case. So does that mean we should give up that entirely, that useful trick? Sometimes it is possible, but when? We have to get to that. Then the next one, interchanging limits. Okay, regarding this one, there are actually two examples. Anyway, let's first see the first one. Limit x tends to 0, limit y tends to 0. What was the function? X square divided by x square plus y square. Now, if limit y tends to 0, then this inner limit becomes what? X square divided by x square, because y square is becoming unimaginably small. Now, note that x, although x is approaching 0, x is not equal to 0. So that's why we can cancel. And this limit becomes 1, or this iterated limit becomes 1. What about the other one? If we change the order, as x approaches 0, x square plus y square approaches y square, okay, which by the way is not 0, because y is approaching 0 is not equal to 0. So the denominator is something, some y square, which is a fixed value. But in the numerator is changing. The numerator is going to 0. So that means here the inner limit is 0. So the outer limit is also 0. So these two values again are different. So that means for this function, the two iterated limits produce different values. Example 1 to 8. Again, interchanging limits. but here the limits are somewhat different in nature. The ones we want to interchange, they are different in nature. And it involves is it 1 or minus 1? 1 or 0? Yeah, it's 1. X tends to 1 minus limit n tends to infinity x to the power n. We have a sequence, okay, but it's not a sequence, a fixed sequence of real numbers. Here there is a variable x, and depending on that x, the sequence will change its character. So before we find this limit, we have to think of what x is. You see, there is a result. In fact, this is where we made the mistake in that example. That result says that this limit is equal to 0 if x is strictly less than 1. Now here this x tends to 1 minus, that means x is approaching 1. Here on the real line we have 1, x is approaching 1 from the left hand side. So we can make x close enough to 1 so that it becomes greater than 0. So x lies in this range. Whenever we are thinking of a limit, we can always think of the limit by restricting the variable sufficiently close to the point at which the limit is being taken. How close, that is up to us. Okay, these vague things that I am saying, all of these things will be made precise when we study real analysis. These things are vague for now because we have studied calculus, not real analysis. So that's why we have a lot of questions with no apparent answer at this point. We are going to give answers to this. So because of this, this limit is 0. So the inner limit is 0, so that means the outer limit will also be 0. However, if we calculate this, x tends to 1 minus x to the power n, x is approaching 1. So x to the power n will also approach 1. Approaching 1 from only one side, that is okay. So in this case, the inner limit is 1, so the outer limit is 1. Here also we get different answers or different results. So how can we decide when we can interchange these operations? So that question remains. We have to answer these questions. Then the next one, to 8, then the 9th example, interchanging limits and integrals. So the further we explore these examples, it seems that our calculus training is going down the drain. It seems that we have actually forgotten calculus and everything is going wrong. So our knowledge of calculus is shaken to the core. So we consider this one. Limit y tends to infinity, integral minus infinity to infinity 1 by 1 plus x minus y whole square dx. What about this limit of an integral? First of all, of course, we will calculate the integral. Now if we calculate the integral, it's not very difficult. If you make the substitution that you consider x minus y to be a variable, since x is not minus, I mean x has 1 with it, so x minus y is just like x. If you know what I mean, that means in place of dx you can write dx minus y, because y is constant. So this integral, you already know the formula for this. This is arc tangent or tan inverse x minus y, where so these limits are infinite, and you know that this is nothing but it becomes infinity, or the limit is infinity when x is pi by 2, or I mean when the angle is pi by 2. So pi by 2 and minus infinity when it is minus pi by 2, minus pi by 2. So this is equal to pi. So that means this becomes equal to limit y tends to infinity, pi is equal to pi. Now we interchange the operations. We interchange the operations and let's see what we have. We now want to calculate this. Limit y tends to infinity 1 by 1 plus x minus y whole square, and we want its integral dx. Now what about the inner limit? You see, if I take y to be infinity, so this x minus y becomes minus infinity. Okay, these are all vague things. Okay, you should understand that this limit will be 0 because the denominator becomes infinitely large. So that means zero. Different answers. What is wrong? Can we not interchange limits and integrals like that? Apparently we cannot. But when can we do that? So the question remains. Example 1 to 10. Next one I think is derivative. Interchanging limits and derivatives. Suppose we want to calculate something like this. X cubed divided by epsilon square plus x square calculated at x equal to 0. So what is the meaning of this? First, we are differentiating a function of x with respect to x, calculating the value of the derivative at x equal to 0. See, because it involves epsilon, ultimately after doing all these things, this will be a function of epsilon. For that function, we are taking this limit. Okay, so for this differentiation, we have to apply the formula for differentiating the quotient of two functions. So let's do that. So this derivative x cubed divided by epsilon square plus x square. This becomes epsilon square plus x square whole square. Epsilon square plus x square, you differentiate this one, 3x square minus, then this one stays x cube times, this one is differentiated, 2x. So here we get 3 epsilon square x square plus 3 x to the power 4 minus 2x to the power 4 divided by this. So that means 3 epsilon square x square plus x to the power 4 divided by epsilon square plus x square whole square. Evaluating this at x equal to 0, at x equal to 0 gives us what? Just put x equal to 0 here, this becomes 0. So for that, if I calculate the limit, the limit is 0. But now we interchange these operations. Okay, so what do we calculate now? Instead of this, now we calculate this. We differentiate this limit. We differentiate this limit and evaluate the value at x equal to 0. So we have taken the limit inside. So if epsilon is approaching 0 from the right side of 0, that means epsilon is positive and it is coming close to 0, then what will be this limit? This limit will be x cube divided by x. Oh, sorry, x cube by x square. Now, this becomes what? X cube by x square is x. Now, this derivative is 1 at x equal to 0, so this is equal to 1. Again, different values. This value is 1, this value is 0. So it seems that limits and derivatives cannot be interchanged. If they can be interchanged, in what case? Then the next one, there are some 1 or 2 more. Example 1 to 11. Interchanging partial derivatives. This one is very important. I give you a function. The function is defined like this. It's partly defined xy cube divided by x square plus y square when the point is not the origin, and 0 when the point is the origin. Okay, we encountered this sort of functions when we study calculus of several variables, right? Now we want to know whether this is true. The second order partial derivative of f this one mixed derivative at 0, 0 is equal to the other one. We want to know this, whether this is true. So let's do it. Here there are somewhat more calculation than the other examples, but this is the one example. After that we have only one more example. So by now our confidence in calculus itself is diminishing. We think, what the hell is going on? Okay, everything seems to go wrong, but the reason things are going wrong is because we are applying things blindly. That's why things are going wrong. Otherwise things will go right. So we will have to make them right. Anyway, so let's first of all calculate the partial derivatives first order. So let's calculate this one. First of all, at a point that is non-zero. Okay, at a point that is non-zero. For that we can directly use the formula. Because at 0, at the origin, the function's definition changes. So there we have to deal with that separately. But at a non-zero point, we can calculate the derivative. It's like this. See? This is the, you see, unlike a function of a single variable, since this is a function of two variables, so the domain will be a part of the two-dimensional plane. Now this is the point 0, 0. Now if I consider a point x, y, where I am trying to find the partial derivative, then I can concentrate my attention in a neighborhood of that point that does not contain 0, 0. So in that neighborhood, the definition of the function is this itself. No matter how close that point, this point is to 0, 0, I can always take a neighborhood sufficiently small which around that point which does not contain 0, 0, so that the function is not this complicated one but slightly less complicated one, this one. So that's why while I calculate the derivative at a non-zero point or a non-origin point, I just have to consider this formula. Now here it's just simply formula for derivative. I differentiate this partially with respect to x. So this becomes x square plus y square whole square. So here I will have x square plus y square. Differentiate this with respect to x. We have y cube. Note that y now is considered constant, minus x y cube times, differentiate this one with respect to x, 2x. So this becomes x square y cube plus y to the power 5 minus 2x square y cube divided by x square plus y square whole square. So this becomes y to the power 5 minus x square y cube divided by x square plus y square whole square. Okay, so this is the derivative, partial derivative of f at a non-zero point. But we will calculate this one also because we will need this one at 0, 0. For this is, here we apply the definition. Limit h tends to 0, f of h plus 0, 0, that means f of h, 0 minus f of 0, 0 divided by h. Okay. Now, okay, so here, now this is a non-zero point because h is not equal to 0. So h, 0 is not equal to 0, 0. So here we have to apply this. Now y is 0. So this becomes 0 after all. minus value of f at 0, 0 is given to be 0. So this limit is 0. Okay, so this is the full partial derivative with respect to x. Similarly, we calculate with respect to y. At first, at a non-zero point, so this will be x square plus y square whole square, x square plus y square. We have xy cube, so that means 3xy square minus xy cube times 2y. So this will be 3x cube y square plus 3xy to the power 4 minus 2xy to the power 4 divided by this. So this is equal to 3x cube y square plus xy to the power 4 divided by x square plus y square at a non-zero point, partial derivative with respect to y. Now at 0, you apply the definition 0 comma k minus f 0 comma 0 divided by k. Now this one, I lost the formula. At a non-zero point, it was xy cube divided by x square plus y square. Now if I put x equal to 0 and y equal to k, this again becomes 0. So 0 minus 0 divided by k. So this is also equal to 0. Right? Now we calculate this one. Partial derivative of this at 0, 0. Here also I apply the definition, but now we are differentiating this function partially with respect to x. So that means limit h tends to 0 del f del y at h comma 0 minus del f del y at 0 comma 0 divided by h. See, this is why we need these values. Now for this one we have the formula. Here we have to put h in place of x and 0 in place of y. Since you see that both the terms in the numerator have y, so when we put y equal to 0, this will become 0, and this, its value is 0. So this partial derivative is equal to 0 because the limit ultimately becomes 0. However, okay, this part, its need is now over. Now what about the other partial derivative? What about this one? Here if I apply the formula del f del x, now we are differentiating with respect to y, so 0 comma k, at 0 comma 0 of course. Oh, I should not forget that one. Okay, minus del f del x at 0 comma 0 divided by k. K tends to 0. Now to find this one, we put x equal to 0 and y is equal to k. Now you see that unlike the first one, now it does not become 0. We have x equal to 0. So this becomes limit k tends to 0. What about this one? K to the power 5 minus 0 divided by 0 square plus k square whole square minus 0. This thing is 0. This one is 0 divided by k. So you see, limit k tends to 0, k to the power 5 divided by k to the power 4 and another extra k to the power 5. So this becomes 1. So that partial derivative is 0, this one is 1. So again, they are not the same. You can verify if you want that the function is differentiable at 0, 0 at the origin. The partial derivatives are also continuous at 0, 0. Not only the fact that they